Okay, welcome to the next part of the additional maths video series. What we're going to do today is related to chapter 16 of the textbook, and in fact we're going to look at a couple of examples from the textbook. And in terms of the syllabus, what we're doing today is really what's listed here. So it's applying the idea of differentiation, so derivatives, that's calculus, and it's specifically to this phrase here, connected rates of change, small increments and approximations. So I'm going to briefly describe what that means, and then we're going to crack on and do 4 examples. This doesn't come up on the exam too much, but there's usually at least one small bit, maybe one part of one question on it in most exam papers. So first, what's it talking about? Well, connected rates of change is very easy to explain. That just means the chain rule. And to give you an example, it means imagine you had something like this, maybe a cube which was growing. Imagine the cube is expanding. Then the cube, here's a cube, badly drawn, but the cube may grow at a certain rate. So it may increase its size over time. It may grow. And that means its volume increases with time. So you might want to know what is the rate of change of volume with respect to time, but you might only know the rate of change of x, where x is the length of one side of the cube. Well, then we could use the chain rule and write dv by dt equals dv, volume, by dx, which is a distance, times dx by dt. So however fast this quantity x is varying, you have to multiply that rate of change by the rate of change of volume with respect to x. Now volume is x cubed for a cube, so dv by dx is just 3x squared. So we see that at any particular point, dv by dt is equal to 3x squared times dx by dt. And it's worth noting, of course, that this equation could be rearranged. If you already knew the rate of change of volume, suppose that was 4 units per second, 4 cubic units per second, and you knew that it was 4 when x was 2, then you could write dx by dt is equal to dv by dt divided by 3x squared, which is 4 divided by 3 times 4, which is 1 over 3. So you can use this, basically what we're doing is using the chain rule as a multiplication law, A equals B times C. So this can be very useful in practical situations. Now let me just insert another page, and let's briefly discuss what is meant by this phrase, small increments and approximations. Small increments and approximations. So what's that talking about? Well, to understand this best, I think you should go back to the basic definition of a derivative. If you have a curve, like so, and you draw what we call a secant line, oops, this might be a bit tricky, there it is. So that's a secant line, or just a line if you prefer. The idea of differentiation was that the gradient of the tangent line, sorry, I'm getting a bit mixed up with my colours, the gradient of the tangent line Oops, down a bit. Okay. The gradient of the tangent at some particular value of x, x0, here's the tangent, and the gradient of the secant line get closer and closer together as our change in x gets smaller and smaller. That's the basic idea, but let's refine it a little bit and consider two values of x, x0 and x0 plus delta x, and assume the curve curves up between these two values. Now we know that if we draw a secant in this case, then we can write something like, well, using the function values, let's sort of draw across here. Here's our y-axis. Here's our y0 and our y0 plus delta y. We can make a simple equation relating delta y and delta x. Delta y is this quantity here, and delta x is this horizontal distance here. So delta y over delta x is the gradient of the secant. But we know from calculus that if the delta x is small, the gradient of the secant is very close to the gradient of the tangent. Now let's emphasize, this is an approximation. That means it's not exactly true, but it's not wrong by very much. So it means that I can replace the gradient of the secant with the gradient of the tangent. But what's the gradient of the tangent? It's dy by dx. So we arrive at this special formula. Delta y is approximately equal to dy by dx at a particular value of x times delta x. So this is the formula that we're going to use to figure out how much y changes. So answer question, how much y changes when x changes by a certain amount. Okay, so that's the basic idea. By the way, the idea is explained in the book. Let me give you the book reference. Well, you can either look at the bottom of page 368, or you could also look at the beginning of the chapter, or rather section 16.3, page 363. And that's particular the section small changes. The beginning of chapter 16 covers the idea of using the chain rule in this way here. Now let me show you 4 examples. Excuse me, we're going to focus a lot more on this one and not so much on this one. So here's the first example from the book. So let me read it for you. Given that y is equal to the square root of x, find dy by dx and use it to calculate an approximate, let me underline that, an approximate value for these two numbers. So because it's approximate, we'll be able to use the principle we saw up here. Okay, so first step, find dy by dx. Well, that's easy. X to the 1/2 gives us 1 over 2 times the square root of x. Okay, so how do we use this for part A? Well, what's delta x? Can you tell me? Delta x is minus 0.04. Minus means going from 4 to 3.96. Now you might ask, what am I talking about? What is the value of x? Well, I'm choosing an easy value of x. And I'm choosing an easy value of x which is close to the number I want. So 4 is close to 3.96. So because 4 is close to 3.96, it means that on this diagram, delta x is a small number. And because it's a small number, the inaccuracy of this approximation will be small. So we get the following. Delta y equals dy by dx at x equals 4 times delta x. Well, dy by dx is 1 over 2 root x. So that's 1 over 2 times 2 times delta x minus 0.04. And the answer is minus 0.01. Now that's delta y, but what was the original value of y? So let's just put a schematic here. X goes to x plus delta x means 4 goes to 4 plus minus 0.04. Y goes to y plus delta y means, now what was y? Y was the square root of x, which is 2. So 2 goes to 2 plus minus 0.01. So the answer becomes 1.99. Now this answer should be given to accuracy, well, we're not told, so that's good enough. Okay, let me just insert a new page. So for, undo. So that was part A. I hope you understood the idea. If you understood the idea, you can try part B on your own and then pause the video and come back. Okay, so for part B we're dealing with square root of 4.08. So again, we're using the formula. Let's remind ourselves. Y equals root x. Choose x equals 4 and y equals 2. Now what's delta x? Delta x, the change in x is 0.08. That's still a small number, so our approximation will be okay. So delta y is 1 over 2 root x delta x. 1 over 2 times the square root of 4 times 0.08 is plus 0.02. So the new y of x equals 4.08 is, sorry, I should not forget to put approximately equal. Approximately equal to 2 plus delta y, which is 2.02. So just to be clear, in the first example, the y of x equals 3.96 is approximately equal to 1.99. Okay, so let's look at the second example. The volume V of a certain gas varies with the pressure P and is given by this formula here. Find the derivative dV by dP, and hence the approximate decrease from as P decreases from 20 to 19.95. And lastly, at the instant when P is 20, P increases at a rate of 3. Find the rate of change of V. So let's insert a page. Okay, so the first thing we have to do is find dV by dP. dV by dP, that's easy. That's minus 600 over P squared. Now let's find the approximate decrease in V. So find delta V when delta P is minus 0.05, and starting from an initial value of 20. So let's apply the formula. Delta V is approximately dV by dP at the initial value times delta P, which is minus 600 over P squared times minus 1 over 20. Okay, so that should be 3 over 2 times 1 over 20, or plus 3 over 40. Notice that V increases when P decreases, which makes sense if you look at the starting formula. Now let's look at part B. When P is 20, P increases at a rate of 3 units per second. Find the rate of change of V. So when P is 20, dP by dt is plus 3. So to find dV by dt, we apply the chain rule. dV by dP, we already know, is equal to minus 600 over P squared, and dP by dt is 3. So that's minus 600 over 400 times 3. That's minus 9 over 2. Or minus 4.5 units per second. Let's check our working. P was 20, increasing at a rate 3 units per second. Find the rate of change of V. Let me show you here. You should understand this meaning with respect to time. That's implied if it's not with respect to anything else. It's with respect to time. Now dV by dP is minus 600 over P squared. We multiply that by dP by dt, we get dV by dt, which is minus 600 over 20 squared times 3, which is minus 4.5. So that's our answer for part B. Here's the third example. This is from an exam. Now here I'm not going to do all of it, but only the focus on part 2. But first we've got to do part 1. the derivative of y can be found using a product rule. X plus 1 derivative times 2x minus 3 to the 3 over 2 plus x plus 1 times 2x minus 3 to the 3 over 2 derivative equals 2x minus 3 to the 3 over 2 plus x plus 1 times, now we use the chain rule, 3 over 2 times 2 times 2x minus 3 to the 1/2. Take out a common factor, 2x minus 3 square root times 2x minus 3 plus 3 times x plus 1. Okay. You can see that the 3's cancel, so we get 5x root 2x minus 3, so k is 5. So we know the value of k, so looking at the second part of the question, we need to find, in terms of p, an approximate value of y when x is 6 plus p, where p is small. So obviously here very important is the number 6. This is our base value of x. So I'm going to start by finding out the value of y when x is 6. Okay, so I get 6 plus 1 times 2 times 6 minus 3 to the power 3 over 2. Well, that's giving me 7 times 27, isn't it? 12 minus 3, 9. Yeah, 7 times 27, so that's 140 plus 49, that's 189. Now I need to, so delta x, what's the value of delta x in this question? Delta x is just p, isn't it? Now dy by dx when x is 6, well, that's equal to 5x root 2x minus 3 when x is 6, which is 30 times the square root of 12 minus 3. So that should just be 90. So finally we can calculate delta y as dy by dx when x is 6 times delta x, which is 90p plus 90p. So the new value of y equals y when x is 6 plus delta y, which is 189 plus 90p, and that's our answer. Obviously it depends on p. So that's how to find, in terms of p, an approximate value for y when x is 6 plus p, where p is small. And I keep forgetting, sorry about this, this is an approximate answer, not an exact answer. And just in case it helps anyone who's confused, let me sketch out what that looks like. What we're saying is, suppose x is 6, we worked out y is 189. Now the curve does what it does. As we go from 6 to 6 plus p, the function increases to a number here, which is approximately 189 plus 90p. In other words, this change is about 90p. So think about it like that. Okay, let's do one more example. Given that y is equal to 1 plus log 2x minus 3, obtain an expression for dy by dx. So using what we've already learned, we know that dy by dx is 0 plus, using the chain rule, 2 divided by 2x minus 3. So for part 2, in terms of p, approximate value of y when x is 2 plus p. So again, delta x is p. Y when x equals 2 is equal to 1 plus log 4 minus 3. And log 1 is 0, so that's 1. And dy by dx when x is 2 is 2 over 2 times 2 minus 3, which is 2. So the change in y is approximately 2 times p. Therefore, the new value of y is approximately the original value of y plus delta y, 1 plus 2p. So I hope those examples made sense. You can review chapter 16 if necessary, and it comes up occasionally on the exam. It's not many marks, but let's say it usually comes up. So I'll leave it there, and I'll see you next time. Thank you.